It is something that at various times we have been doing it in different names, namely the teaching young graduate students some of the basic stuff that's going on perturbative QCD. I mean, it's a very long program. I see a lot of young phases simply because we started about 25 years before actually. What is called QCD at LHC or something like that, in that some name. LHC is to attract people. QCD is QCD is LHC is a QCD machine. So it was actually intended to understand physics at QCD through understand physics at LHC through QCD processes. And when I started as a practitioner in this area, there were very few people, okay, and we were only few, and particularly in perturbative QCD. I can give you a little history. I started my journey here and as a graduate, and my area of research was QCD. And when I started, there are only few like Ramesh and Murthy. They are professors, retired now, and then Shaurendra Gupta, and few like them actually do really doing something related to QCD actually. And the area was also very limited, in the sense actually there are not too much developments, because it was quite young that time actually, in the 80s and 90s. And after that, because of various experiments, and people started taking it very seriously and wanting to do computations in QCD. And now the area is really quite big actually. There are dedicated meetings on computing things using very sophisticated mathematics, because it has developed to that stage actually. Okay, so from 80s and 90s we have been trying to organize schools at every stage to teach young people to what is QCD and how it is useful in the context of experiments actually. That's some goal of this entire program actually. We do all these calculations to understand some physics that is happening at various experiments, and experiments also feedback tell us what to compute and what to compare and things like that. So in that sense actually this in India elsewhere actually this area developed now so much that nobody talks about basics of QCD now. It's more about calculating Feynman integrals and how to apply modern mathematics to compute things. And this computation also led to questions like what are the universal structure of case theory, because SU3 is actually one of the beautiful case theory that in physics in nature you can realize, and also just replacing 3 by n you can actually understand the structure of SU and case theory as such. So in that context people have studied not just the importance of SU3, importance of SU and group, or the underlying structure of case, whatever beautiful structure that you see. You will see that these calculations not only actually led to understand physics, like to discover Higgs or any particles that we that nature admits. It also led to understanding the case theory or quantum field theory of whatever the physics that we study. So it has got two phases. One is to understand experiments, and in the process of understanding we understand the theory itself actually. Okay, theory itself is so deep. It has very beautiful structures, and understanding this actually leads to questions in related field theories. Okay, so I would say this is one field theory where it talks about reality, and it also contains lots and lots of interesting structures that in fact helps to understand something which is beyond this theory. Okay, so I would say it is important that answer questions in related to experiments, and also try to understand what is the theory that explains and what that theory contains actually, because it's very important that we understand the theory itself. So it's a two-way process, it just feeds into this to understand. My first lecture is about, I'm going to take you a very short journey of 4 lectures or 5 lectures. Okay, how asking questions in various stages in strong interaction physics actually led to identifying the right theory of strong interaction, okay, namely this QCD, and then what QCD actually gave us to understand the physics, because you start with asking questions, and then you find the right theory. The theory itself actually gives you quite a lot of things for our understanding. Everything may sound abstract now, but as I go along, you will understand how the theory developed and what the theory gave back us actually in terms of understanding physics as well as theory itself. Okay, so my entire course, whatever 4 lectures, many of the seniors know everything. Okay, I don't know why they are sitting here, but this is for sort of targeted to the youngest audience actually. Okay, so let me just begin by asking questions about why you want to study QCD, or why you want to study this field theory that I am talking about. Okay, so the topic that I want to study is strong interaction. So where do we see strong interaction? Of course, we all know that strong interaction we see when you study nuclear physics, when protons, neutrons, the fusion, fission, and so on and so forth actually. Okay, so I will go beyond that aspects of strong interaction physics. I want to ask a very simple question that if you see in extended objects in nature like proton, neutron, and things like that, how do I understand this structure of this proton, neutrons? For example, if I have a proton, neutron, etc., these are strongly interacting particles. Okay, of course, pre-QCD there were many theories that explained how these particles, okay, they interact among themselves, or how the interaction between them. There are models related to these things actually, but I'm not going to details of those models because those are all predated, and I don't think there are now interesting things that is happening here. Okay, but I wanted to sort of ask the question actually, what is this proton is all about, or any such particles in nature, strongly interacting particles. Okay, is there any fundamental theory, okay, like QED, that can actually allow us to explain the existence of such particles and how they interact with each other and so on and so forth. That's the kind of question that we want to ask. Okay, once you say these are all extended objects, that's what the experiment tells. It's not that theories come and tell protons are extended objects. It's an experimental fact. When you do scattering experiments with protons, one finds that the protons are not point-like particles. They have some structure, in the sense it is like if you bombard an electron with an electron, you can confidently say what is their their extent, that in the spatial extent, by looking at various distributions in the final state. Similarly, if you perform an experiment with protons and neutrons, one finds the extent in which they actually spread in space is not point like, it is actually, it has a specific. So you understand that they are all not point like particles, they are in extended objects. Once you realize they are extended objects, you would like to know what it is made up of, whether it's just some charge distributions, the kind of questions when we asked about atoms, we want to ask the similar questions, whether these are all point like they are made up of some some further simpler point like objects with certain distributions and things like that. A priori we the simple scattering experiments are not going to tell you how it is going to be like that, but we'll have to do very sophisticated experiments. Okay, so the first experiment which can actually sort of started probing the structure of protons is what is called elastic scattering. Like in if you really want to understand structure of anything, it is better you just use some probe that we have complete control over, and see what it how it reacts, and from the reaction you can actually find out the structure of proton. So this simplest experiment was elastic scattering. What is elastic scattering of this? So you actually take electron, okay, and then bombard this on a proton or target containing protons. Okay, this is just a reaction, and then look at the final states. Okay, proton will go to proton, electron will go to electron. If such a thing happens, you say it's a elastic process. Okay, you can also produce some other particles. It's okay. Okay, still it is elastic. Okay, so this momentum I call K, and momentum I call P here. This is K prime, and this is P prime. Okay, because they will change momentum, energy, whatever. For momentum, it will. So this what is there is all for momentum. Okay, so K actually means K mu. Okay, so it is like a K0, K1, etc. Okay, so this is what I mean K mu. Okay. See, if I have instead of proton electron, okay, we have QED to compute this process very nicely. We can just draw Feynman diagrams for this, because we understand how electron interacts with another electron or a positron, and then we can compute in QED using perturbability methods. Draw a set of Feynman diagrams and compute what is the amplitude for this process. We can compute the scattering cross section for this process, or you can also look at distribution of this final state. After scattering, in what momentum regions they can actually populate, in what angle they populate more or less. All that information can be obtained by looking at the standard approach called scattering theory. Okay, so the scattering theory will tell you how you can compute cross sections and things like that. So let me call this cross section is d sigma. Okay, sigma you all understand, it is, I mean everybody has studied first course on quantum field theory, so this is quite familiar to all of you. So this process, if you want to compute, we need to actually have a scattering of this. This is the lowest order Feynman diagram that you can write. I take this liberty to write down Feynman diagram for this, because if I accept that proton is charged particle with a positive charge, then the interaction between electron and proton, okay, will be electromagnetic in nature. So without really asking any questions about what this proton is all, just using this this electromagnetic property of proton, I can straight away write down what is the interaction of these two particles and sketch what a tree level scattering amplitude. Okay, because I checked this proton not a point like, so I put some blob, okay, just to show that they are extended objects. Okay, and write down what is the scattering of this. So this is typical Feynman diagram, lowest order Feynman diagram that I can write to describe this process. Actually, here I am not asking any questions about what this proton is made up of. All I know is it has an electric charge E. If somebody gives me a two charge particles, I can always write down amplitude of this kind. Now you can also add diagrams. We have an exchange of another photon, or proton can also emit. If it is accelerating, you can emit photon. Quantum field theory allows before scattering or after scattering, emission of photons, because proton is a charged particle. It has every right to produce any number of photons. Okay, that is clear. So this is the lowest order diagram that you can draw. Okay, what is the use of this diagram? Now, if you can calculate, I'm just dropping other higher order diagrams, because if you restrict yourself to, let's say, if this is E and this coupling is E, and then it is order E square amplitude, and then the square of it will be E power 4. Okay, so you look at only the amplitude that is the lowest order in certain parameter. Here it is a electromagnetic coupling constant. Okay. Now, what is the use of this experiment? You perform this experiment. All I can do is actually I can prepare proton and collide electrons and look at the final states of these electrons, E minus K prime. Similarly, you can also look at the final state proton, which comes with momentum P prime, and you can study by calculating various angular distributions or energy distributions of final particles, and see whether it has any resemblance with similar scattering where proton is is replaced by muon, okay, or any other point like objects. So that will tell you this is anything special, proton is anything special other than having just electromagnetic properties. Okay, so that's an idea that if you want to study that whether the proton that we are trying to understand has anything more than what we all know about, that it is a charge E and it interacts through exchange of photons. Okay, so this is one of the earliest experiment to probe the structure of a proton. Okay, and here there are no strong interactions. Okay, it is just purely electromagnetic. So I use some known physics to understand some unknown physics. The unknown physics here is strong interaction. Okay, so that was an idea behind it actually. Okay, so you can actually do this in the following way. So you write down your matrix element and then calculate the amplitude square. I put bar here because you need to actually sum over all the polarizations, average over initial polarizations, and sum over all the final state polarization. That because you have an experiment where you are not interested in polarizations of or spin configurations of initial and final states. So you need to, by putting bar, everybody knows what we are doing. It's just summing over final state, all possible polarizations, and averaging over initial state. So this is what you want to compute first before we really substitute in cross sections. So we all know how to compute cross sections. I don't have to teach you this. So when you try to write down in quantum field theory, you will get stuck at some point. I'll show you where exactly you'll get stuck, and then and that will help you how to resolve it actually. So this average over will be 1/4 because it is two charge spin off particles, and sum over final state SI, all the spins, and this is what it means. Okay, this is the amplitude for a process of this kind. Okay, and you can have an amplitude with two particles in the final state, and you can have an amplitude, different amplitude with three particles in the final state, and so on and so forth. All that is contained here actually. Let's do honest to good computation just using the lowest order. Okay, and this is justified because the coupling is so small, we don't have to worry about it. You will see that this kind of approximations will not hold good in QCD. Okay, so it's so simple. You can write down the amplitude sum over SI. Okay, so this is U bar, K prime, S prime, and gamma mu U of K, S. This is about your initial states, that initial lepton. And what else? You have a propagator here, like a minus G mu nu by Q square plus I epsilon. I'll ignore this I epsilon, wherever it is allowed. So U bar of the square of it actually. Let me just carefully write down. So let me just write down the amplitude and then square it actually. Okay, sum over this. So mu. Okay. This is my amplitude. This is about this part of the amplitude. You start with the final state and then go to this. So this is your amplitude, and here is the propagator, where q is actually k minus k prime. This is the momentum exchange, and this is the corresponding propagator. And the J that I have written down here is the one that I really am interested in, because I can draw this diagram very happily because I know this is electromagnetic interaction. But if I want to write down the amplitude for this, p goes to p prime, a proton going to proton, where momentum is initially p and then final, I don't know how to write down because nobody gave me a theory for the theory of protons. All I know is it's it has charge E, probably some mass m, okay, etc., etc. But I don't know how to write a term like this. I don't know how to write down the wave function. This is like a polarization of your Dirac wave function. No, this is how you expand your Dirac field in terms of polarizations of this Dirac whatever spin polarizations, u and u bar, some basis. We don't have such expansions. You can write some capital U, but we don't know how to compute that capital U for proton, because we don't know how to solve this Schrodinger equation or Dirac equation for this proton, because we have not understood. It's not a point-like objects. We cannot apply the standard Dirac equations and the interaction of this photon with these things. So it is so all the ignorance about the proton, how the photon interacts with the proton, that vertex that I have written down here in QED, it is this vertex. Okay, this is what you call interaction vertex. Okay, and the psi you can expand in terms of u and u bar. Okay, but that I cannot do it for proton. So I just call this whatever psi bar, gamma mu psi, or corresponding one like capital U bar, some, I don't know what that gamma means actually. It is some complicated looking function here, and another capital U, I don't know, that is also another complicated. Everything I put everything together and call it as some J mu actually. So at the moment, as a theorist, I cannot do beyond what I have written down here actually. This is again a lowest order expression. Of course, this you can have more contributions, because you have I have forgotten to put here some IE here. So you will have terms which are higher order in nature, because you can have photon exchanges, photon emissions, and so on and so forth. But this ignorance will be always accompanying you at every stage actually, that about what proton is all about. Okay, so what is the next step? I mean, of course, with unknown I can actually proceed and compute. Okay, but of course I cannot tell the experimentalist what the cross section is from theory. Okay, so I just leave it at that stage, saying that okay, I accept that now I don't know how to parameterize this. I don't know what this is all about, but I will continue with this unknown function, unknown current J mu. But all I know is actually it's a function of the momentum of the incoming proton and the outgoing proton. Instead of writing P and P prime, I have written in terms of P and Q, because it's all same. You need only two momenta to describe this. Okay, so this is what is called a current, electromagnetic current. But current which I don't know how to describe in terms of polarizations of the proton, spin polarizations like u and u bar or Dirac wave functions. Okay. So, how do I proceed actually? So, to proceed, okay, I am going to use again some of the symmetries that I already have in this theory, namely this entire process is actually dictated by U1 symmetry, okay, and that U1 symmetry implies that actually these objects transforms like a vector, okay, because this is a interaction is a vectorial, not axial vector or some more complicated ones, tensorial or anything. So, the simple property that the interaction is vectorial in nature, and this J mu can be parametrized in terms of vectors available in this part of the amplitude or amplitude square. Okay. So, I am going to just use this property that it is a vector, Lorentz vector has a specific transformation properties, okay, and I am going to exploit that. Using that, I am going to do this. Of course, you should not forget that if I have a polarized scattering instead of unpolarized, where I sum over all the polarization of the incoming proton and the outgoing proton, then if I don't do this, then this J will also contain information about S. Okay. Then I will have 3 momenta at my disposal to parameterize this J mu or J nu here, using that actually. So, since I am considering unpolarized scattering, I have only 2 momenta at my disposal. So, how I am going to write down J nu. So, instead of working with J nu, I am going to work with some scalar functions, because I already know that this can be expressed in terms of the momenta available. Okay. So, the simplest way is actually I take J nu p comma q. As I said, I am not worried about the spin part, because I am summing over all the spins. So, I do not need to really worry about spin part. Okay. So, this can be written down as let me just put tilde, because I am going to use J later on. Tilde is also for because this is in momentum space. So, you need the appropriate symbol will be this. So, I am going to make a following decomposition of this, just using the properties of this okay. So, I can keep writing actually what are the terms q square, q, u, etc. Then u of p prime. Okay. These are these 2 polarizations. So, all I am doing is actually I want to imitate this, because it is also fermions, and in the case of QED with electrons, this is completely dictated by your gauge invariance or whatever, gauge symmetry, and here of course this is a this is again QED, so there is some gauge symmetry is there, but the structure of this this vector, I have to sort of carefully write down these indices. So, I call it as mu. It is not dictated by any U1 kind of symmetries, because this is a current where it can be a function of P as well as Q. So, these are the possible vectors that I can write down actually. So, what are the vectors that I can write down actually? That I use this gamma mu, psi bar gamma mu, sorry, u bar gamma mu u, it also transforms like a vector. So, that is one possible vector that I can use with a coefficient, unknown coefficient f1, and I can also use this product of 2 gamma matrices contracted with q, which is also which also transforms exactly like a vector under Lorentz transformation. Okay. This combination is also vector, even though it is made up of 2. You can also have 3 gamma matrices, 4 gamma matrices, and so on and so forth, but gamma matrices beyond 2 can always be simplified and written in terms of a single gamma matrices, single gamma or gamma mu, gamma phi kind of things. So, having more 3, 4, 5 etc. with contracting some q can also be written down, but all of them can be actually rewritten or expressed in terms of sigma mu nu. So I will show one such identity later on actually, how 3 gamma matrices can be written as a single gamma matrix, and gamma 1 gamma and gamma mu gamma phi. Okay, so you should not wonder that why I did not write 3, 4 gamma matrices. So all of them can be combined, and you can also write something which are without gamma matrix. This is q. Okay, and I have not put p or p prime here. Do you know why? P is also a vector, which Lorentz vector. I did not put p or p prime separately because when I said this is electromagnetic process, like this vertex and this vertex also current is conserved, which means if I take a q mu and act on this current, that will be identically 0 every order in perturbation theory, because this is an electromagnetic process. I am not talking about how this photon interacts internally with any other particles inside. Proton is treated as a charged particle, with like a ball, tennis ball, it's charged. Okay, p, if you put p or p prime and multiply q mu, p dot q is not 0. Okay, so I'll have to be extremely careful about not putting q, but this term I am allowing actually q square, which means if I allow this, then there must be something wrong. So I'll have to just using current conservation, whatever this current conservation means, actually q mu times that vertex, that full lower part of the amplitude is 0, tells you that terms of this kind actually I can drop, like p or p prime and so on and so forth. Is this clear to everybody? Okay. So I'm sort of left with only few terms. Okay, and this is called the electric form. This coefficients which I have written down f1 and f2 now contains all the ignorance about the object that we start with, this proton here actually. Okay, I don't know, if it is point like, I can quickly write down it is I times E, because it's not point like, I don't have freedom to write down. Yeah.
That can depend on P dot Q, right?
Exactly. So now that is where I wanted to come. This Q is what actually? It's actually P square, P prime square and P dot Q. Okay. So this, the coefficient, once I said it is it transforms like a vector, all the coefficients have to be scalars, Lorentz scalars. Lorentz scalars, it can be constant, just some number, and also can be a Lorentz scalars of the vectors that go into this. So it will be p square, q square and p dot q, right? These are the only possibilities actually. Is that correct? Okay. So this is in an elastic process. You can actually relate p prime to p dot q, no? Because its final state momentum is completely dictated by these things actually. So you can actually parameterize only in terms of one invariant actually. That is a speciality. Okay. So this q square is sufficient. You don't need. So if you have a p and p prime, so what are the things? P square, p prime square, and p dot q. I'm calling this p dot q is q square. So that's only invariant. P square and p prime square are masses. As I said, it can depend on some some constants. Constants, not in Lorentz sense, but some properties of this. For example, in this case, they are masses. This is m square. This is also m square. So I'm dropping those simple constants here. Okay, I'm keeping only those, terms that are sensitive to this momentum transfer here actually. Okay. So in principle, as Saurabh was saying, any fi will be a function of fi m square comma whatever p dot q or q square. I will use q square for convenience. Okay. So that's all about these things. So as I said, it's called electromagnetic form factor FF. Okay. This is called anomalous. Anomalous part. We will see why it is called anomalous part. Those who have studied, Dirac theory, even in free theory, if you not free theory, interacting theory, if you start computing radiative corrections to, this electromagnetic vortex, you will find that when you go beyond leading order in perturbation theory, you will start developing a term of this kind, which comes because of anomalous magnetic moment of the electron. So this will be proportional to square of the electromagnetic coupling constant. They are generated in the theory. If you write down, is this familiar to all of you? Anomalous magnetic moment. It comes because of interaction. Otherwise, tree level will have only this vertex, and when you take into account radiative corrections coming from photons, this will give you not only this. If you write down your current after taking into account one loop corrections or two loop corrections, you will find there will be corrections of this kind where F2 can be determined completely within QED. Okay, unlike QED with protons with non-trivial structure, we won't be able to calculate it from theory. Hence, we actually express them in terms of some unknown form vectors. Yeah.
U bar and U both are function of P prime. One will be P prime, another will be P.
Which one? P. Okay. Sorry. Thank you. Correct. Okay. So that is the first part that I wanted to say, and let me just. So I'll just proceed. Having sort of parameterized, that's the first step that we can cross one hurdle actually, where you now have a not the vector to deal with, but only the scalar functions to deal with actually. Okay, okay, let me just proceed further. So you compute cross section. This is d sigma. You have proton and electron. So you write down your flux vector. This will be like 4 times m times the energy of incoming lepton, and then you write down matrix element square, which I have written down here, and then you write down the phase space for this k prime 2 pi whole cube to k prime 0, and phase space for proton prime 2 pi cube 2 prime 0, and then this energy momentum conservation delta function delta 4. Okay, this is your phase d sigma. I didn't put integration because it's just d sigma. Okay, so all you need to do is actually you compute this matrix element, substitute this into this, contract all the indices. Now take the trace, because now you have parameterized in terms of some simple polarization, what we call spinors actually, u bar and u of the proton. Hence it is computable. All we can actually conclude is actually it's computable, but it is expressible in terms of only these unknown quantities like F1, F2, F3. Okay. So you can do this exercise, but I am not going to do this contractions and etc. etc. But if you do this algebra and to do this algebra, then you need to worry about how to deal with this quantities. Okay, so you all know this, you study these things, dqp, nep or p prime, let's say p0 prime, you can write it as 2 pi whole cube d4 p prime delta p prime square. If there is a mass m square, you can write it down like this, and theta of p0 p prime 0. Okay. This identity you are all familiar with actually, because if you integrate p0 using this delta function, you will get back this. Okay. The p0 prime, we all know that actually is square root of p vector prime square plus m square. Okay, so this is on shell. Okay, so all these p prime 0 are all known in terms of the other components and the mass. Okay, so you can do this algebra very easily. Okay, that is something that you can try yourself. Okay, so I will not do that part, but if you perform this, you will find very simple looking expressions. Namely, if I compute, if I call, I'll just write down k0 as k mu as k0 0 0, let's say k3, and I call this k0 is e, and similarly k prime 0 is equal to e prime. Okay, just parameterize like this. One way of doing is actually you consider proton and electron in the center of mass frame. So you'll have a e minus and p, and demand if suppose this is k and this is p. Okay, write down k as k0 0 comma 0 comma k vector modulus. Okay, and then suppose you choose along this is like a z direction. Okay, and then you can write p as p0 comma p0. This will be again minus k vector. You can parameterize in a simple way, and similarly after the scattering, okay, they will go like this. One will be k prime, other will be p prime with an angle theta. Okay, so you can write down the remaining components. So that will help you to actually sort of solve this. So the first thing is actually you substitute here and take care of this delta function. This 4 delta function will go away. So you will be only left with the dq p prime, which is easy to handle if you actually do this computation in center of mass frame. Okay, so that's not very difficult actually. Okay, maybe for completion I can write down what is this k prime 0. So if it is along z direction, this phi in 0, so you can write it down. This is sin theta cos theta, and I have to be careful actually. K prime here, similarly k prime here. Okay, this is your parameter. The other one p prime is actually k plus p minus k prime. So just using the simple looking parameterization 2 goes to 2, we can actually try to simplify this 2 body phase space. That's straightforward. Okay, so this is all given in textbooks. You can also reproduce all of them. I will just write down what would be the final result, because there's a lot of interesting things in that. Okay, so d e prime. I should tell you what is omega. Omega is actually whatever. Okay, this final state angular part actually. This is d omega. This is the energy of this final state. This is your differential cross section. Okay, and this differential cross section you can actually calculate. It doesn't take much time. And this is q power 4, which actually means q square power square. I'll be careful about this, and I can write it as GE of q square. I'll tell you what these are all. Minus q square by 4m square. This is doable, very easy computation. 4m square into cos square theta by 2 plus minus q square by 2m square into gm of minus q square sine square theta by 2, and everything is multiplied by nu minus q square by nu plus q square by 2. So, I am not introducing any new notations. So, it is as simple as this. Of course, you have more terms if you include 2 photon exchange and other radiative correction. This is a tree level calculation. Okay. So, what are these GE and GM? GE and GM are actually related to, I will explain to you what these things are. So, as I said, this is just a solid angle. I have already written down, which is written in terms of the final state particle. So, alpha here is E square by 4 pi. E is the electromagnetic coupling constant, and with this kinematics you can write down minus q square is 4 e prime sine square theta by 2. Okay. So, it depends on, as you know, q is actually k minus k prime. So, if you calculate q square and ignore masses, like if you ignore k square is equal to 0, k prime square is equal to 0, because in this calculation you can drop electron mass completely, because it just will hang around, but it is compared to the rest of the kinematic invariance, these quantities are highly negligible. Okay. So, also to look at some structure, drop all those which are irrelevant okay, numerically also. Okay. This is minus q square is actually simply proportional to the energies of this and then the angle action. Okay. This is a very important quantity, and here nu is actually p dot q. Okay. Just dot product. Okay. So, in terms of this, I have written down some shorthand notation for this minus GE q square, which is simply f1 tilde minus q square minus some kappa times plus q square divided by 4m square f2 tilde minus q square. This is one term, and then another term which is another linear combination is f1 tilde minus q square plus kappa f2 tilde of minus q square. Okay. So, kappa is some constant that you can actually compute using this. Very good. This is all you can get. So, as a theorist, you can actually go up to this stage and say, okay, I raise my hands and say, beyond that I can't do much, because what else you can do actually beyond this? You can write down your differential cross section, which depends on the solid angle omega e of the scattered particle and its energy. Rest of them I have integrated out, because 2 into 2 process is all you can do. And right hand side you can see that we know what E prime is. If you perform an experiment, you can find out what is the energy of the particle that is produced. You know what is the momentum transfer, because if you know the difference between initial and final momenta, you can compute this quantity. Okay. All the constants you can compute, invariance, everything except these 2 quantities. You can also measure angle actually, at what angle actually you can actually see. Yeah.
Real or complex?
This quantity.
Peptide.
Oh, real.
It cannot be complex.
The way it is parameterized, you can actually pull out. If it is complex, you can pull out. So it's. I have pulled out, IE and things like that in that current actually. Okay. So you can keep doing this, and then you will end up this where you have two unknown functions instead of f1 f2 tilde, just for simplicity. For some reasons actually people have expressed them in terms of, instead of f1 f2 I can write it in terms of g and ge and gm. This is just some linear combinations. You don't have to pay too much attention to this. Maybe those are very easy to measure because they are proportional to cos square and sin square. Some number, some constant actually. There is simply in terms of this invariance.
Invariance as in there's no q square dependency.
There is no q square dependency to this. Okay. So now at this stage I will leave it to experimentalists to go beyond and tell me about these functions. That is all we can do, because I started with a proton and I accepted that I don't know everything about proton. All I know is actually how the current looks like in terms of few unknowns, and these few unknowns are also functions of some invariance. That is also understandable. And then just by doing some simple honest to good computation to lowest order in QED, this is what you get actually. There is no strong interaction, nothing. Okay. If there is any strong interaction that we want to capture, that's all of them should be contained in this, this cheese that I have written down here. Okay. Now what you do, you just compare this, just compare this with data, real data on scattering of electron and a proton. Look at the angular distributions along with the energy. Okay. Given energy E prime or E and E plus delta E, yeah.
So one comment. Actually, why people initially didn't thought of that proton? They must have thought it. So treat it as a point particle and compare with the experiment and put a overall factor, so that
the overall factor that you are talking about is this actually what I am doing. What overall factor? See, you suppose if you have a current J mu, instead of writing J mu is actually some overall factor times point like J mu, I am doing a little refined that's exactly this. No, if it is not just simply proportional to J mu electromagnetic current with the one unknown function. There are more unknown functions, not only f1, you will also have f2. That's the whole idea. Is this clear? So it's not one function that is sufficient to parameterize all the ignorance actually. You need two functions to parameterize your ignorance about the proton. Okay. You will see that actually there may be more also, okay, depending on it's only one or two here because I assumed that this coupling is electromagnetic. Okay. If it happens to be weak interaction, weak interactions, electroweak interactions, you can also have a Z exchange or W plus W minus exchanges. If I have such exchanges, then this interaction of Z particle with the proton will be not only electromagnetic, it also could be parity violating, right? If it is a parity violating interaction, then it will have a more opportunity to probe the structure of proton in a much better way. Okay. So people have done such experiments also to probe the structure of the proton. But I will restrict to the simplest one. Historically, people who looked at only simple ones like a photon exchange and study. Is this clear to everybody? Okay.
So if the proton is actually could have been a point particle, then the form factor should be 1.
Exactly. You can already identify actually, even if you if it is a point like particle, what G and Gm would be. As you correctly pointed out, that if it is a point like object, the way it is parameterized in such a way that f1 will be just 1 and f2 will be 0 at tree level. When you compute f2, if you do radiative corrections, you will find f2 will be non-zero. That is why the name comes. It is called anomalous part of the current actually. Anomalous part means tree level current will be just psi bar gamma mu psi, u bar gamma mu u with a constant coupling E, but if you calculate one loop radiative correction, you will find, you all must be familiar with G minus 2. G minus 2 is a very important quantity. This is one of the first evidence of quantum field theory. Schwinger computed this, and now this is known up to 5 loop level actually, and this is very important quantity in physics actually, G minus 2, which tells everything about your QED. Okay, so that is this G minus 2 part actually. This kappa that is related here, I've written kappa here, it is actually 1 or off or whatever. Okay, and if you calculate in QED, this one, this half will get corrections. Okay, so let me just go ahead. Yeah.
Happened to the linear net field.
Sorry, linear?
Net field.
Yeah.
Cross section I would have expected to be quadratic. Is there some
Quadratic, yeah, I think it is quadratic. I'll just you're right. G square, yeah. Which is big actually. Yeah, it's actually squares actually. Yeah, that's correct. So you can actually somehow, okay, so there is some modular square or something like that. I'll just come back to this actually. I'm changing the notations here, somehow I copied wrongly. Okay, so now you compare this with the experiment actually, okay, and look at the, for example, the data on d square sigma by d omega e d prime as a function of cos theta and e prime or q square. Okay, you can look at the data and try to extract these functions, this gm, which is written in terms of the form factors. These names are called form factors actually. Maybe I should tell you, these are called form factors. Okay, you can extract this form factor squares directly from the experiments and then see how they look like as a function of q square. Okay, because it's only function of q square. So this data that you get from comparing this will tell you whether your this form factor that I have written down here will raise or as an increase q square, or it will fall off as an increase q square, or it will wiggle around, or it will have some non-trivial structures actually. So it tells you how the E that you see in electromagnetic case, how that E, one constant now is no longer E, it is actually some kind of a quantity that is a function of q square. Okay, that's so really looking at the form of the this form factor, we can actually find out how this this extended objects look like in the eyes of this photon carrying this momentum q. Okay, so that's something that one can actually do. In fact, people found by just fitting the data against this formula, the gm okay, just write down some fit people have made. You don't ask me how how good the fits are, okay, at something like this actually. Okay, but there are very advanced this is fit, so it's not derived from any specific theories actually. So it goes as minus q square whole square, okay, in some sense. So as a function of q square, moderate q square, you don't really take very large q square, and moderate q square so that proton remains proton, it doesn't break into pieces or get destroyed. Okay, I'll come to that topic next. If you do this experiment, then the comparison of this your prediction from theory, modulo this unknown functions, and comparing this with experiments, what you find is actually these unknown functions GMs, they go as this 1 by up to some dimensionful quantities, because these are dimensionless. So I've dropped all the dimensionful. This 1 actually means some dimensionful quantity, okay, in units of q square. It goes like this actually. So behavior is actually, if you have a momentum transfer which is very large, okay, then the form factors actually fall off very nicely. Okay, it falls off as 1 by q square. Okay, so this tells you about if you think of F1 as some kind of a charge that is sitting here for the simple electromagnetic case. Here, in the case of proton, it's also kind of a charge distribution. As you probe more and more, the photon sees less and lesser of the charge of the proton. Okay, so it just tells you that it is not a point like, it has some distribution of charges actually. And you can also show that by integrating this form factors, you can get what is the total charge and things like that. So it actually is a measure of how charge is distributed inside the proton. Similarly, this GM also tells you about how the magnetic part is distributed. So this is how people found actually that proton is not a point-like object. Proton is not like it's not a point-like, but it has a non-trivial charge distribution, electromagnetic charge distribution, not any other charge. Okay, this proton. So this is one way of actually understanding the proton and some moderate energies where you have this elastic type of scattering experiments. Okay, so people after understanding this wanted to actually also go beyond this this simple looking picture and see what happens if this is a point like Thomson did. Thomson broke this atom into pieces and study electron and proton. You can actually do more sophisticated Thomson type of experiments and see whether one can actually break this and check whether there is any internal structure. Okay, that was the next step actually. So the first step is actually to really do a very humble exercise of not really disturbing the proton, just beyond changing its momentum. You extract whatever information that you get. So this exercise was one of the first exercise which were done in the context of proton by looking at what are called form factors, and that's the outcome of this actually. Okay, so this is there is a lot of literature about how GE and GM looks like, and people also started modeling this GE and GM using certain models. You can think of some models that actually collection of particles or some specific charge distribution and things like that, and try to see whether some models can actually reproduce those data. Okay, yeah.
What is the scale up to which this is valid? You don't disturb the.
Okay, what is the scale that the proton doesn't get broken into pieces and things like that? That's not very it's not very sharp. Okay, range if you for example in if you say minus q square, okay, this is the you can think of minus q square is the energy square that is transferred into this. Okay, so if you do an experiment with about 10 GeV square or 10 or 15 GeV square or more, then you can start seeing the fragments of the proton actually. Okay, so there is this. Where is 10 coming from? It's not coming from theory, of course. Okay, so the point at which it breaks, I think it is not dictated by theory. I don't think it is coming from any theory or anything. Okay, so this short boundary where proton actually breaks into pieces. Okay, I will come to this, why there is no sharp boundary and things like that when I study this, what is called deep inelastic scattering experiment. Okay, that is my next topic actually. Yeah. Yes.
If F is a function of q square, should not we expect proton's g factor to be dependent on q square?
Which g factor?
Proton's g factor.
G factor?
Of proton.
Proton. What g factor is this?
G minus 2.
Oh, g minus 2. Yeah, it depends. You are talking about these corrections actually. Protons. Protons, of course, it will have a q square dependency. The g minus 2 that we are all talking about is not about proton, it is about leptons. For example, muon g minus 2 or electron g minus 2. Those are about point-like particles. You can compute them in theory explicitly. Here you can't compute. It depends on all these factors.
Typically, g minus 2, g does not depend on the scale, right?
Typically, it means what?
I mean, for leptons.
For leptons, it doesn't depend.
Proton, if we can calculate, it will depend on the scale.
Sorry?
If we calculate it for proton, it will depend on scale.
Okay, so this statement is also, I'll come back to this. For example, g minus 2 is g minus 2 at lowest order is 0. Okay, so if it is non-zero, it can come only from quantum corrections. Quantum corrections are proportional to coupling constant alpha, for example. Strong, in this case, it is this fine structure constant alpha. This these corrections are proportional to, let's say, constant times alpha square, and so on and so forth. All these alpha are defined in a particular scheme. Okay, if you choose the scheme where alpha, like a Thomson limit, okay, then all these alphas are constant, right? It's 1 over 127 or 137 or 127, depending on what scale that you are looking at it actually. Now, if you expand in powers of ms bar alpha, then this g minus 2 will start depending on q square also. So it depends on which scheme you actually compute this terms in perturbation theory. Is this clear? So it's not, when you say constant, it is in a particular scheme that you look at it actually. So otherwise g minus 2 is a series expansion. In any series expansion, if you truncate, it will be but it is a physical quantity. If you sum all of them, it will be independent of scheme and so on and so forth actually. Yeah.
So is the fine structure constant.
So is the fine structure. Okay, that is fine. So now my next task is actually, I want to go beyond this and see. Someone asked actually, I start increasing. If I have a knob, I can start increasing this q square, and at some point, this scattering is no longer elastic, but it will be inelastic. What inelastic means, instead of having just one proton, you can also have bunch of other hadrons, leptons, and so on and so forth. Which means actually I reached sufficient energy to break this proton because proton is not like point-like object, so I can break it. So all I have to do is actually just, instead of this p, I will have some p, and then instead of this, I will have px. X is the collection of some final state particles, which contains everything that is possible. It could be leptons, it could be proton, neutron, pion, lambda particle, and so on and so forth. So I'll put more lines here, and I call this as px. I call this as px. So this scattering is called deep inelastic scattering, because for some reason it is inelastic, and since you are probing deep into the proton, you call it as a deep inelastic scattering. And reaction is more like this, where x, as I said, it's a collection of some particles. It could be something proton, neutron, lambda, pi, blah 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 blah, everything. Okay, and I want to look at exactly the same thing. Okay, but now I cannot use the same approach here, because it is not about the current for this. Okay, you have a bunch of these things. It will be sensitive to X. X could be 2 protons in the final state and something else, or 3 protons and some 5 leptons and another muons. Okay, charge is conserved anyway, so you'll have to be worried about all that into account. Then it will be very, very difficult to write down a current which contains some final state particles with a specific number. Okay, so the current the one that I wrote down, J mu, is more like is related to some matrix element of some J operator, where proton goes to proton prime. This is what I wrote down as J mu. Okay, but now in the amplitude, if I want to take P to Px, this Px could be 2 protons or 3 protons, 1 lepton, and it is impossible to actually write down an equivalent of this for a deep inelastic scattering. So that is the first difficulty that I will encounter. Is this clear? Okay. So for deep inelastic scattering, I need J mu operator with Px, where Px could be any set of hadrons and leptons and so on and so forth, because when proton breaks, many things can happen actually. Okay, that's this. So it's very difficult to compute such a current, and I need to sum them up all, and writing down in terms of form factors will be extremely non-trivial task. I don't think that's worth doing it. So I will not follow these steps and try to extract anything like form factors and things like that. But there is an alternate approach to this, which goes by the name, instead of form factor, there is something called structure functions. So that's my next topic. Maybe another 15 to 20 minutes. I will just illustrate how this can be done in a very systematic way. So this board I can continue to use, or there is something more than this actually. I can use this board. There is some.
Maybe 5 minutes.
Yeah, 5 minutes. Finish. I will finish. Thank you. That's also blackboard, no? Where is the blackboard? This is whiteboard. So I have to use whiteboard, is it? Okay, I prefer to use blackboard anyway. Huh? I will erase it actually. No, it's okay. I just sorry. So how I'm going to do this deep inelastic scattering. I'll just describe in 5-10 minutes actually. Okay, so I'll use the same board. I'll just remove some parts. I think I don't know if this can be used or. So I'm going to do this actually. So I want to proceed it exactly in the same way. I want to compute this square of this amplitude, sum all the final states. Basically I need to sum not only the spins of this final states, all the momenta, because the particles that are produced are large in number. I want to sum them up actually. Okay, I'll tell you how theoretically this can be done very easily. Okay, even though you don't know what these particles are all about. Okay, and this is the amplitude square that I want to compute actually. Okay, so how do I compute this? So let's write down how it looks like. This is exactly the same thing that I want to do, and this you can write it down as P prime by E. I'll explain to you at some point, maybe in tutorial or whatever, how this comes about. All square by minus q square plus square. I'll tell you what this is. W mu P comma Q. I'll explain to you how each term comes about actually. Just look at this process like this. Okay, and take the complex conjugate because you are calculating this m square. Just put like this. It's more like a mirror image. You take a complex conjugate. This is P. This is P. This is Px. This is Px. This is Q. This is momentum. All that. This is K prime. This is also K prime. This is K. K. This is what you are doing. This actually is just a complex conjugate of this. In the approximation that I made, I'm dropping all the terms. Okay, the following thing will work. You can actually separate out the top part of this diagram like this, and then the lower part of the diagram, and write it as the product of two quantities. Because if you just make a contraction, this part is just the propagator square. If you put it, that comes from here, and then the upper part of the diagram I call it as L mu nu, because this will be mu index. Let's call this is nu, and let's say this is say mu prime and mu prime, and this is mu prime, and this is chi nu prime. So if you do a proper contractions, all you will get is actually some L mu nu and d mu nu. So the upper part is called L mu nu K comma Q. As you can see, upper part depends only on K and K prime. Instead of writing K and K prime, I write it in terms of K and Q. So this is simply half of, because one lepton, sum over final state spins S1 and S2. Okay, I'll neatly write down U bar K prime S2 and gamma mu U of K of S1 times same thing K prime S2. I call it as nu this is your L mu nu. It is just a square of the top portion actually. This times complex conjugate of this. And what about W mu nu? W mu nu is little complicated. So again W will depend only on P and Q. I am going to tell you why this X is missing here, because it is a scattering where I sum over all the final states. Okay, so sum of Px has to be summed over, like I sum over all the polarizations. Okay, so what is this as actually? This will be 1 by 2 pi times 1 by 2 m times sum over Px sum over S averaging and P comma S current J mu 0 . This is your lower part of this amplitude square actually. Okay, so it's basically it is exactly if you just replace by your proton by electron and this Px by electron prime and substitute, you will get exactly the same result that you wrote down in the previous case actually. Simple. Okay, this J nu is just simple psi bar gamma nu psi in the case. But you don't know what psi is actually. We don't know how psi acts on proton. All that we don't know. Formally it is a current which is more like a psi bar gamma nu psi, psi bar gamma mu psi. And Px is actually, these are two operators that are sitting here, and you calculate the matrix element. This is just a complex conjugate of it actually, because J is real. So I just put J mu instead of putting J mu star. And when you take a complex conjugate, it just Ps goes that way, x come here actually. So is this clear? It's just square. And since you are calculating a cross section where you sum all the final states, spin, all that, this px is summed over. It's basically sum over all the final states. If you write down in this language, sum over all final state means you not only p prime is integrated out, you integrate out all the px. It will be product of all of them. So in short notation, sum over x actually means integral over p prime I p prime I 0. This is the product of a given I number of final states. So you have all possible things, 1, 2, 3, etc. So all i's have to be summed over for all. Okay, it's more like that actually. It's just for a given n number of final state, it's just a product of that measure, and it's not just one, it's all possible. You can have 2 particles in the final state, 3 particles, 4 particles, and so on and so forth actually. So it is just all sum of all possible final states. So that is what this summation indicates actually. Okay, so that's clear to all of you, and you will see that if I substitute, calculate everything, this delta function will play an important role to get your final amplitude. So it is just one step before getting u bar u in any derivation of to get amplitudes. Okay, because I don't know what j, I've just not proceeded further. This is 1 by. This is just a normalization because if you carefully write down your amplitude, the normalization of PS will be proportional to 2m times delta cube or something like that. In field theory, the normalization of this will have some 2m. Even in canonical commutation relations, you have some dimensionful quantities, something like this actually. So just a normalization. This pi is also neatly distributing these pi's in various places. Okay, it is just writing an expression in a elegant format actually. So j mu is a current, and then the j mu of x will be e power I p operator times x, j mu of 0. Do you know what it is actually? How this comes about? Sorry? Somebody said something. Okay, so this p is an operator, okay, and if it acts on some state n, it will give you some p, small p, times p times comma n. N is some other quantum numbers. So this is something that I am going to use here. Tell me what it is actually. You all should know. The last bench actually. The T-shirt, blue color. The U only. So this is something I should not forget actually. If sum over px equal to 1, and there is equivalent representation in terms of momenta also, this completeness relation actually. This also means actually all one particle, 2 particle, 3 particle, everything. This has a nice expression expression in terms of this dp's. It's just putting this d cubes and integrating them will give you 1 actually. Okay, so I'm going to use this is the starting point for writing down. 5 more minutes I'll finish actually. I'll just stop at some stage so that it will be easy to read. So now L mu nu is called the leptonic tensor. Okay, that's the name for it. leptonic tensor. Okay, and W min is called the hadronic tensor. It is obvious, I don't need to explain why it's leptonic, it's hadronic. L mu is calculable because this part of the diagram is, everything is known. The vertex is known, all the polarizations are known, you can compute this square, this into this. So it's calculable. Hadronic part on the other hand is not calculable because we don't know what J mu. We don't know what is the structure unless somebody tells me, it looks something like this, I cannot calculate. Even if somebody gives me some J mu, unless I know how J mu acts on Px or how J mu acts on P, I won't be able to calculate these quantities. As far as I see here, actually J mu is some operator current, some unknown current, and it is sandwiched between two states. One is Px, other is P, and until I know the matrix element, I won't be able to proceed. But let me see how far I can proceed, and then the way that I did it in the previous case. Let's proceed and see how much you can simplify here to get to the form that we can do further manipulation. Okay, that's my start. I'll leave it at that stage actually. So we can do the following simplification. J acts on Px, this J also acts on Px. Okay, let me see whether I can somehow manage to sum this Px by using this, this J mu of x is equal to this quantity. So all I do is actually I replace J mu of 0 by this identity. J mu of 0 can be written as e power minus. This is a simple exercise, you can try this. Okay, Ps like J mu of 0 Px, I write it as Ps. P is the momentum, S is the spin. Okay, so this is e power minus P dot x. Okay, J mu of I, J mu of x, e power I P dot x, Px. Okay, then you can find out what is this P acting on this. This will be Px. The P acting on here will be just simple P, and you can pull out these two out. Okay, that will be some exponential of something. Correct? And replace this delta function. So you do this for this first one. So the exponential will be e power minus I P dot x plus I Px dot x. This is the first part. And 2, this delta function 2 pi whole power 4 delta 4, okay, q plus p minus px. You write in terms of some d4. What will I write actually? Some psi or something like that. Okay, e power I. You choose your these things. Because this is some identity of this kind. You just substitute here and try to perform the sum over Px using this identity. Okay, so these two steps will allow you to use this identity because the dependency on x actually goes away from this this currents, and then you can straight away write down use this identity between these two currents and put that to be 1, and you can get an expression which is, I will probably do it in one of the tutorials. Okay, it will be simply 1 by 2 pi equivalently. This part I can also write it as, I'll show that later on. You can also write it as some okay, because you can show that the second part that I have subtracted is identically 0. Okay. So this is a kind of a representation of this W mu hadronic tensor in terms of the currents that I don't know what it is, sandwiched between two proton state, but it is not a local, it's a bilocal actually. It's some object called J mu multiplied with another J nu. They are in two different space-time points sandwiched between proton state. This is called, you know, hadronic tensor, and our next task is actually to proceed further using again some symmetries, parameterizing them in terms of another set of functions which are called structure functions, not the form factors, because it is not about amplitude, it is about the cross section, as you can see, because this W mu nu comes after squaring your matrix element. In the previous case, the F1 and F2 they were actually were parameterizing the amplitude, not parameterizing the cross sections. Now at this stage you have cross section already, you are looking at the cross section, so this W mu nu appears in the cross section. Okay. So if I want to parameterize them in terms of, you know, momenta and stuff like that, okay, the functions analogous to this F for G, they are called structure functions. So this the name is different actually. So that I will do it in the next class, how to proceed further and express your cross section in terms of some unknown functions called structure functions, and what these structure functions tell about the proton that we have actually made broken into pieces actually by elastic, this inelastic scattering. So I will stop here. Maybe this exercise either we can do it in the tutorial, or if you want to do it privately also you can try, and then if you have doubts you can ask me. It's very straightforward. Just you have to use this identity and this. That's it. Okay, I'll stop here actually.
Cheers. Thank you. चालू है रिकॉर्डिंग मेरे साथ मूव करता है क्या अभी ऑफ है राइट अभी ऑफ है So this one, right? This is the
No, this is yes, right? Oh.
yeah, it says, but I don't know. The switch also? Okay. नीचे से आ जाएगा पहुंच जाएगा आवाज पहुंच जाएगा अभी ऑन है क्या कैसे कैसे बंद होगा shall we start or wait हमारे ऑर्गेनाइजर्स तो बाहर हैं Shall we start? Okay. So good. I think good morning is still good morning to all of you. This is the second lecture of the school after Ravi. So let me thank the organizer first for scheduling my talks or lectures conveniently or according to my convenience, and also basically they gave me freedom on choosing the topic because it was difficult to prepare something on short notice. Okay, so what I have planned to cover in this 3 or 4 lectures, we'll see, is to talk about some technical aspects of one loop amplitudes, which are important ingredients when you want to make very precise predictions for experiments, collider experiments, where you collide 2 particles and you are interested in making certain observation about final state particles. Okay, so Ravi has already introduced one process which is probing the structure of proton, and as you have learned by this time that this you can do at high energy by colliding particles, right? So one of the basic experiments in high energy physics to understand nature at very small length scale is to collide particles. So for example, if I collide E plus E minus, what I am interested in what are all possible final states. Okay, for example, I can have say E plus E minus, I can have mu plus mu minus, I can have photon photon, and there are several such possibilities. Okay, and by studying actually such processes or looking at particular final state, one can infer the nature of interactions. Okay, so the basic observable you can say is for a given final state particle, which is actually the cross section that we are very familiar and Ravi has already introduced, and this quantity, the cross section for a given say final state, say E plus E minus to some final state, is proportional to the amplitude square, right? And this amplitude square is basically gives you the probability of observing that particular final state among all these possibilities. Okay, so that's what basically this quantity is effectively doing, and so it has actually more phenomenological interpretation, but for us in this lecture what is going to be important is understanding the basic structure of amplitude in perturbative quantum field theory. Okay. So in perturbative quantum field theory, this we can organize the amplitude in terms of Feynman diagrams. Okay. So this is something we know from the first course in quantum mechanics, and for that all we need in our theory is some small parameter, which often is a coupling parameter. For example, take the QED, where the interaction vertex is denoted by this kind of an interaction. Electron interacts with a photon, and we can actually represent this by a term like IE gamma mu. Okay. So once you know the interaction, you can describe any process diagrammatically. Okay. So for example, in QED, if I want to describe a process E plus E minus to say mu plus mu minus, which we often end up computing in the first course in quantum field theory at tree level. So what we are talking about, we want to understand this process, an electron, a positron, and I want to look at mu plus mu minus. And on the right hand side, I want to know that what theory has to say about this blob. Okay. So perturbatively, what you find at the lowest order, you have this. Okay. So this is E plus E minus mu plus minus. Please just understand that, which is mediated by a photon. And if you look at the coupling parameter, this appears at order E squared or alpha, the finite structure constant. Okay. So if it is the lowest order, you can actually continue by just following this rule, that by vertex I mean 2 charged particle and 1 photon. Then you are going to basically draw at higher order this kind of a diagram. Say for example this, or for that matter, which I should draw for the sake of completeness, this, and several other. I mean, these are just prototype things. And what you notice that these are actually order E, 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 so E to the power 4, and therefore they all appear at order alpha square. Okay. So and you can continue. What is going to happen? You are going to basically say, for example, at order alpha cube, you are going to come across, say, for example, this kind of a diagram. Let's just again respect the vertices, and that's what you are going to come across, right? And what you are noticing as you go on higher and higher in alpha, you basically come across these loop diagrams. So, for example, at order alpha, I do not have any loop. At order alpha squared, I come across 1 loop diagrams. At order alpha cube, I come across 2 loop diagrams, and you can imagine you are going to come across higher and higher loop diagrams. Okay. So at this stage, what we want to understand, how the loop diagrams, they are different from the tree level diagram. So if you ask this question, if I know what is the momentum of the initial particles, electron and positron, then in this tree level diagram, because at every vertex what we have learned, the momentum is conserved, therefore the momentum of the internal line here is P1 plus P2. So both are incoming, which I denote by capital P. Okay. So since I am performing the experiment, I know what is the initial momentum, and since I am observing the particles, I know basically what is the final state momentum. But in this tree level diagram, just by the conservation of momentum, I know what is the internal momentum of or the momentum of the internal line. Let's ask the same question in one of these one loop diagrams. Okay, and whatever we discuss at the level of one loop, this is going to be basically applicable to 2 loop and higher loops as well. So for that matter, let's look at this part of the diagram, what I have. So I would have basically this as capital P, this also capital P. Now the question is, what is the momentum of these internal lines? Okay, and all I know basically that at every vertex the momentum has to be conserved. So I do not know what is the momentum of this or this. So let me assume that the momentum of this internal line is L, Now the moment I do that, I immediately know that the momentum of this is p plus L by the momentum conservation. Okay. So the question is, what is exactly L? Okay. When you ask this question, so here the internal line momentum is completely fixed, but here you have an arbitrariness. L could be anything. L could be 0, L could be some finite number, any finite number, or for that matter infinity, any indefinite number. And for all this, there is no problem, because the momentum conservation tells you that this would actually hold. So what this actually loop diagram is telling you, that the loop momentum or the momentum of the internal lines, they are not actually well defined. They can actually carry any value, 0, finite, infinite. Okay. And this is very, so you can actually imagine that this diagram is actually set of diagrams with different values of L, and quantum mechanics tells you that you should basically sum over all. It's equivalent to basically summing over path in position space when a particle goes from one point to another point. So naturally, quantum mechanics tells you to sum over all possible L values. Okay. And if you since this is basically a continuous variable, this summation over L results into an integration over 4 momentum L. Okay. And you can imagine this is what is going to happen as you go on higher orders. So for example, if you go to say at order alpha cube, where you have got 2 loops, you are going to come across 2 such integrals. Okay. So something like d4 L1, d4 L2, and so on. Okay. So this is the say basic difference between tree versus loop diagram, where loop momentum is indeterminate. You don't know actually what values it has. So this is supposed to be integrated out whenever actually you have any such diagram. Okay. So what I want to do, I want to basically write down the expression of this amplitude to continue the discussion on loop amplitudes. Okay. So this is one of the actually simplest one loop diagram. More complicated, so which involves basically 2 propagators. If I were considering this, I will come across a loop diagram, one loop diagram with 3 propagators, and here I have an example of one loop diagram with 4 propagators. Okay. So let's actually first look at these integrals. So if you apply the Feynman rules for the vertex, what you come across this kind of expression for this amplitude, which is you'll get a trace because of fermion loop L slash plus m. So let me say index is mu and nu. This is mu L slash plus p slash, where by L slash I mean L mu gamma mu. Okay, that's the notation, slash notation, plus m gamma nu. Okay, so these are 2 vertices, and these are actually fermionic propagator, so they have got numerator, and then I get in the denominator L squared minus m squared plus I delta L squared plus p whole squared minus m squared plus I delta. Okay, this is what basically the expression of this one loop amplitude is. Okay. Now if you have learned actually trace algebra, then you know what you're going to come across. You are going to come across terms involving 2 loop momentum in the numerator. You can come across one, in the numerator 1 loop momentum and no loop momentum. So something like this, L mu, L nu, or say L mu, or just 1. These are actually 3 possibilities for the numerator, and the denominator is this, which is loop, and I'm going to basically just use a shorthand notation for this kind of term as just d0 and d1 for this, where d1 I mean I have added basically a momentum here. Okay. So this is so there is a classification. We basically call the one loop integrals where loop momentum appears in the numerator as tensor integrals, okay, because of this structure, and if you don't have any loop momentum in the numerator, we call them as scalar integrals. Okay, so that's the classification. And in an amplitude, you expect that they are actually contracted with either external momenta or the polarizations. So, in general, when you solve one loop diagrams, what you can come across, the most general one loop amplitude where you have n such denominators, okay, which I am going to denote as actually d0, d1 and so on up to dn, right? And you can come across some, say, m such numerators, mu1, mu2, mu n. Okay, so it's an n-point function because it has got n propagator. That's the terminology actually we are using, and of an tensor with rank m. Okay, in renormalized gauge theories, you come across where m is always less than or equal to capital N. Okay. And these integrals, they are actually not, they are ill defined because, as I said, this loop momentum which you are supposed to integrate, it can actually take any value. Take, for example, the scalar integral, which is 1 over L squared minus m squared, L plus p squared minus m squared when integrated. So, if I consider the large momentum limit, okay, these masses and the momenta, external momenta, they are not relevant. So, the integrand actually behaves as L squared. Okay. And what you have here d4L, so naively it goes as dl over L in the large L limit, okay, which is logarithmically divergent. Okay. Now, this where actually, now you can imagine that as far as the other two integrals are concerned, the tensor integral with rank 1 and rank 2, they are going to be basically divergent. For example, the first one is linearly divergent, the other one is naively quadratically divergent. Okay. So, what we are dealing with, we are dealing with inherent divergences in the evaluation of loop integrals, and the question is how to basically make sense out of these integrals. Okay. So, the way actually these integrals are handled, we use a mathematical trick of regularizing the integral, which is basically the process of, that's how basically in mathematics they are, for example, they are example of improper integrals. So, improper integrals, they are defined by making the limits finite, evaluating the integral, and then taking the limit in which your limits actually become infinity, and if they exist, if the integral exists, then that's a convergent integral. It doesn't exist, that's basically a divergent integral. Yes.
So people, when they started to add this loop computation historically, so they taken this mass part, like if there is a massive propagator, they have taken it. So initially I just want to think, and you gave the analogy of path integral with this, why they didn't attach any other aspect like spin with that I mean that internal propagator. I have like
so they are actually there. So actually what happens, if you look at the definition of the propagator, the numerator of the propagator is basically sum over the polarizations. So for the case of a scalar, that is 1, but for the case of actually fermion, this L slash plus m that you are looking at, it is actually sum over u bar. Okay, and for the say vector particles, this minus g mu nu, that is basically sum over the polarizations. So the propagator does actually carry the polarization or spin information as well. It is there. It is basically part of basically every numerator. If you basically write down the same thing for a graviton, you are going to basically appropriate factor you are going to basically write in the numerator. Okay. Okay. So so the question is basically what do we basically mean by regularization? So there are several ways of regularizing it. I would actually limit myself in these lectures about the dimensional regularization, which is an efficient way of making the divergent integral finite and then extracting the divergences out of the loop amplitudes. Okay. So we will see that it's a very useful mathematical trick which satisfy actually certain properties, and the properties that we will be using heavily while understanding the structure of one loop amplitude is linearity and translation property. So for example, by linearity I mean that in D dimension A L plus B G of L, okay, this becomes DDL f of L plus B DDL G of L. Okay, and the other property which is actually very important is the translation. So f L plus P is equal to DDL f of L. Okay. This translation or shifting of momenta, it can be done only if the integral is finite or convergent. Okay. In divergent integrals, you cannot basically shift the variable. Okay. It basically leads to some additional terms. So these are the basically two properties. One of these is crucial, is this shifting of the momentum. Remember that when I am actually in D dimension, meaning I am not actually in D is equal to 4 dimensions, then my integral is finite. Okay. So with this axiom, we are working and evaluating the various loop integrals. And what is expected, that since the real world is D is equal to 4 dimensions, as I go to the 4 dimensions, I will basically see the divergences appearing. So for example, often D is taken as 4 minus 2 epsilon. Okay. Just taking example from here, for example, this is a logarithmically divergent. If instead of actually 4, I am little below over 4, then in large L limit this would be basically finite. So with epsilon greater than 0, what I expect that as I go D to 4, which basically means epsilon going to 0, I would basically come across divergences which appear as pole in this epsilon. Okay, so this we will see explicitly in a few cases. Yes.
Can you repeat that statement that you cannot always shift the momentum?
The shifting momentum.
Yes.
Yeah. So the point is like. So the question is. We basically often do the shifting of variables, but remember that when you do the shifting only in finite integrals. Okay, if you do it in divergent integrals, then you have to basically come across additional terms. Okay, these are known actually boundary terms. Yeah. So, but if you switch to D dimensions where your integral is finite, then this is basically a property or an axiom. We are saying basically that now shifting is allowed. That's what this statement is.
And is the linearity also only for the convergent integrals, the above state?
So I'm not actually 100% sure because as I said basically that even when you say deal with improper integrals, you don't basically deal with the limits which are exactly infinity. For example, 0 to infinity, and some integral basically I have f of x. The way it is understood is that you have something like this. You basically look for existence of this kind of a limit. Okay. So the moment, so you always actually deal with finite integrals. Okay. And for this, yes, linearity does hold. So let me take up a simple example. A simple finite
Integral or integrand? If the
integral, the full integral.
I mean, sometimes the full integral is still diverging.
Yes.
But still we do shifting for the virtual part of the loop integral.
So if your integral is not convergent, then shifting basically would result shifting. So see the I mean you do the shifting because it is invariant. That's what you want, invariant under shifting. But that is true only if the integral is convergent. So we can take up actually an example in tutorials and see basically what happens. So for example, that's the reason why cutoff regularization, which is also one of the very popular way of regularizing integral, is not preferred over dimensional regularization. Okay, so I just want to quickly take one example which I think is part of the textbook of solving this kind of integral, and the purpose is just to review what goes in evaluating an integral in d dimensions, okay, which is divergent. So this integral, which you can actually also find in the Pechkin and Schroeder, is d for L 2 pi to the power 4, which is for the normalization 1 over L squared minus m squared plus some I delta. Okay, so this is a simple one loop integral where there is only one propagator, and this is quadratically divergent in 4 dimensions. Okay, so what I want to do, I want to shift this to d dimension as a process of regularization. Okay, I'm going to put basically this tilde to put this 2 pi to the power 4 factor, which will become 2 to the power d factor, inside this. Okay, just to save time. And this is L squared minus m squared plus I delta. Okay. Now what I also want to do, because when I shifted into d dimension, I have changed the natural dimension of this integral to make sure that integral still remains its natural dimension is maintained what it is actually in 4 dimension. I multiply with the dimension full parameter to the power minus mu square to the power 2 minus d by 2. So this factor I have introduced just to make sure the natural dimension of the integral is maintained, and you will find basically this is the factor which will appear all point scalar integrals. Okay. For example, I mean although we are dealing with strictly with the amplitudes, but what you are doing basically, you are doing the full theory in d dimensions. In fact, your Lagrangian action, everything is in d dimension, and there this guy gets introduced to ensure that the coupling parameter, which was scaleless or dimensionless in 4 dimension, that still remains actually dimensionless parameter. Yes.
Written with mu square, and like even in the divergent integrals you told that all of them diverge with alpha square. For the up to the for e cubed you know that the diagram which you get, the amplitude is 0. So what about like e power 5, e power 7 or something? How do we know that there's no diagrams at all for that?
There are no
diagrams in order e power 5, e power 7.
No, but there are actually. This is an infinite series.
No, we don't alpha power. We said different. You said different loops are different powers of alpha, not different powers of p.
Oh, you mean okay? Okay, I see. Yeah, right. Yeah.
So for 3, that triangle diagram, like the amplitude goes to 0. But like, how, is there some way we can show like 5, 7, and all also? There's no diagrams.
Right. So the point is, I mean, so for example, I mean, to understand when you are organizing this amplitude, okay. So the coupling, the power counting in coupling, that is actually dictated by number of vertices that are present. Okay. So the process I described is actually a 2 to 2 process where I need at least 2 vertices to have a diagram. Okay. And if you want to basically don't want to change the final state, meaning basically you want to remain 2 to 2 processes, every loop means adding actually 2 vertices.
Are there any processes where I would have like e power 5, e power 7? There are processes.
Your triangle diagram, decay and things like that. One particle going with 2 particles.
In triangle diagram?
You can have a triangle diagram. Something decaying into 2 particles. If
Okay.
you have 3 vertices, e cube. e power 6.
No, the triangle diagram, like the amplitude is 0.
It's amplitude.
Not always 0 actually.
Oh, it's not always.
Yeah. But for example, what Ravi was describing, or in the context of the process we have considered, you can basically also, there is a reason to look for this process, okay, to make a very precise prediction. And if you draw this kind of diagram as a leading order, this is one of the diagrams which is relevant as this. So you, yeah, so you at the amplitude level you will come across this odd power. Okay, so observables would be amplitude is square, so you will come across even powers. Yeah. Okay. So yeah, so we want to basically now look at this integral, and so I can in d dimension basically I can break into two parts. For example, d L0. Remember that the space, we are in Minkowski space, right? So I need to basically deal with L0 and the other space components differently. They are not actually on equal footing. So what it means basically, I have mu square to the power.
In the denominator there is
So let's see, actually d is equal to 4. This is fine.
yeah, but 1 by L square, and L is the dimension of mass. So and mu is also dimension of mass. So in the denominator, if you see, it's a mass square, but in numerator it's mass.
So this should have basically mass square dimension, right? This should have mass square dimension. So all I have done basically, when I shifted to d dimension, this has changed, right? And I want to ensure that this plus this gives me mu squared.
L is scaled by mu.
Oh, so this is fine? Okay. We can check, yeah.
L is scaled by mu.
So v square so mu dimension is 4 minus d, right? And L dimension is 3. So natural dimension is 4.
Right. Okay. So if I break this integral into the space, time and the space component, I mean although I am in the momentum space, what I have is L0 squared minus L squared minus m squared plus I delta. Okay. So what I have basically, I have actually poles in L0 plane, which because of this plus I epsilon prescription that you have learnt in your first course in quantum field theory, which is used basically to make the integrals convergent, it also basically maintains the causality. Okay. So this basically tells you that in L0 plane the poles are shifted. Okay. So there are two poles, L0 equals the square root of L squared plus m squared minus plus delta, this is plus minus. So this one is actually here and this one is here. Okay. So you can apply the technique of contour integration, because in the large L limit, you know, this actually goes to 0. So you can actually solve this in two steps by integrating over L0 and then by basically taking this in spherical coordinates in momentum, and that's what you get. But what you have learned basically that this can be done in single steps if you, instead of working in Minkowski space, you work in Euclidean space, and that is, for that you can actually do what is called basically Wick rotation. Okay. And under that, what you do, you basically L0, identify L0 with I L0E, okay, so that L squared becomes minus LE squared, okay, and your integral minus infinity to infinity L0, that actually goes to I d L0E minus infinity to infinity. Okay. So this step is crucial. You see that I have not changed the limits of so the limits were minus infinity to infinity. The limits are still minus infinity to infinity, while you would expect that when I do this kind of a variable, my limits basically should go to the imaginary line, right? But you can actually show using the property of contour integration that so you can, when you do the Wick rotation, you can actually choose the contour which is like this. Okay. which doesn't actually cover any pole, and that's how you can actually connect. And these parts, as you know, they are going to basically give you 0 in the large L0 limit. So this part is going to get connected with this part. So I leave this basically as an exercise. You just try and show that this statement is indeed true with limits minus infinity to infinity, not minus I infinity to plus I infinity. Okay. So this basically allows me to do everything in one go. What I have now is let me call this integral, this part of the integral. Let's not worry about this as I. And what I have, this integral I is minus I minus infinity to infinity d-dimensional integral in Euclidean space divided by, okay, that overline notation, divided by LE squared plus M squared minus I delta. Okay, that's what you have. And this now basically I can solve in spherical polar coordinates. I can write this as my 0 to infinity dLe LE to the power d minus 1 times the angular part in d minus 1 dimension, right? It's like r square dr d omega, which is basically d theta d phi, but you are in d dimension. So the angular part is here, and this is nothing but the sphere of the unit volume. Okay, so by using the property of Gaussian integrals, you can show, maybe we can, if you want, we can discuss it in the tutorial. This in d dimension is given by v of d equals 2 pi to the power d by 2 gamma d by 2. Okay. So that's the angular part, and what you are left with this part. So my integral I becomes minus I v of d 2 pi to the power d 0 to infinity, and I'm going to basically so what I have, basically I have got my variable as LE, and here I have LE square. So what I'm going to basically convert everything in LE squared. Okay, so d LE squared to the power d minus 2 by 2 divided by LE squared plus M squared minus I delta. Okay, so now the full integral is in terms of variable LE square, which I can denote as x, and this is 0 to infinity half dx x to the power d by 2 minus 1 divided by x plus 1. Okay, where I have defined x as LE squared over M squared. Okay, so I have taken actually M squared outside. That basically gives me, that ratio gives me x. That basically goes here, gives me another x, and here basically I multiply and divide by M square. So I will get an overall factor of M squared to the power d by 2 minus 1. Okay, so that's what your integral is, and this is nothing but, this can be expressed in terms of beta function, Euler beta function, which is given by 0 to infinity dx x to the power a minus 1 plus x to the power a plus b. Okay, there is another representation which is another variable from 0 to 1, and that is given by gamma a, gamma b, gamma a plus b. Okay, so that's the formula you basically apply, and you get the simplest scalar integral with one propagator as minus I M squared minus I delta to the power d by 2 minus 1 mu squared to the power 2 minus d by 2 gamma 1 minus d by 2 divided by 4 pi to the power d by 2. Okay, that's what the answer is. Okay, and following basically the same, you can actually solve a more general integral, which I would like to give you as an exercise, and that is something like ddl L squared to the power n L squared minus m squared plus I delta to the power capital N. Okay. Same thing, everything actually goes smoothly. As you can imagine, the difference is only n. That doesn't change anything whatever you have done. You have another L square which appears here again, that actually becomes one variable. Yes? So, sorry? There is no? Oh, right. So, yeah, you actually, yeah, do it this. Put it here, absorb here. Okay. Okay. So, see this integral, because whatever has gone into it, one needs to basically evaluate other scalar integrals with higher propagators. Some additional actually steps are involved, but the point is, when you solve that integral, this is a you always come across this step where you have to eliminate the loop integral, and the process is exactly the same. Okay. In more complicated integral, after even removing the or integrating out the loop momentum, you will have another integrals left over to be done. So we will see probably in one of the last lectures how to evaluate those integrals as well. But the purpose of doing this exercise was to basically review the basic step of getting rid of loop integral, which is a very common procedure. Okay. So, having this, what I have basically the expression of this integral in d dimensions, and if you put d equals 4 minus 2 epsilon, okay, what you get an expression like I over 16 pi squared m squared. We can actually, I'm directly writing this expression because I believe that one way or the other way you would have done this if you have done first course in not sure actually, but if you have done basically vertex correction or these things, you would have. Otherwise we can actually take it up. This is putting the values and then seeing how these terms actually arise, especially the most interesting part, 1 over epsilon minus gamma e plus 1 minus log m squared divided by 4 pi mu squared, and then I can basically have order epsilon term, order epsilon square term, and so on. Okay, so that basically you basically get an expansion in epsilon, and what you have come across, this 1 over epsilon, is basically a reflection of the fact that in epsilon tending to 0 limit, this is a divergent, and that divergence is exactly the divergence that we said at the loop level. So, as long as you don't, I mean, just to emphasize that regularization is basically making the integral finite, and the idea is that with this finite integral, you do all the calculations, get to your physical observable, and then at the end of the day you set epsilon to 0. This is nothing actually different, because we have come across this while dealing with plane waves in quantum mechanics. The one way to normalize plane wave, because it's not normalizable, is to do box normalization, and the idea is that you place the plane wave inside a finite box. Okay, imagine that it has got a length. You do all the calculation, and at the end of the day, when you are done with computation of probabilities or say expectation values, you set that L to infinity. Okay, and that's basically how you set that plane box normalization works. It is basically exactly in the same spirit. So as long as I don't set basically epsilon to 0, everything is finite. Okay, so the question is, I have looked at basically this. We have already seen I can come across integrals with 2 propagators, 3 propagators, 4 propagators, and on top of that I can have these objects like loop momentum appearing in the numerator. So the question is, the basic question is, do I need to basically evaluate these loop integrals every time I come across one while studying a particular process? Okay, and in this course we are going to learn, no, this is not the case. we are going to basically understand this structure and see that we can organize our calculation in such a way that only finite set of integrals needs to be computed for once and all, and depending upon actually your process, you basically just use those results and put them back when you want to basically make a prediction. So this statement actually heavily relies on a feature which is again very much visible in dimensional regularization, is called reduction. Okay. And what this reduction is about basically how to deal with tensor integrals, meaning integrals which have loop momentum in the numerator. Okay. So let's take the example where I had one loop momentum in the numerator and then d0 d1. Please remember the definition. d0 is L square minus m square, d1 is L plus p squared minus m squared. This is just to basically save time. And so this is what basically the integral I have. Okay. So I can actually directly switch to d dimension because it's a divergent integral, because b0 is already divergent. This is actually linearly divergent, so there is a reason that I do everything in d dimension. But we will clearly see that why it's again actually just to emphasize that why this doing this process is important in d dimensions. So the statement that I want to actually write on this on the right hand side, that what this integral could be. So let me denote this by b mu. So b0 was the scalar integral. This is a one rank 2-point function with two propagators. It's just a notation, and I want to ask that what is actually on the right hand side. Okay. The d1 has the momentum p. Okay, and Lorentz covariance tells me that on the right hand side I can have anything which is of the vector type. Okay. Since L is the momentum to be integrated out, the only thing which can basically serve this purpose is p. So I can write fairly that p mu times some coefficient b1. Okay, where I know that b1 has to be basically a scalar, meaning it can depend upon p squared, m masses, and so on, right? So, and this step has nothing to do. So this is true basically in 4 dimension as well as in d dimension, but we'll see basically where the d dimensionality comes into the picture. So now if you agree with me that this integral can be basically written in this form, then we can do actually something to find out b1, what this b1 is. And what do we do? So what I can do, I can actually multiply both the sides, or contract basically this equation with p mu. Okay, and if I do that, what I get in the numerator here is L dot p, and denominator I have d0 and d1, and on the right hand side is p squared times b1. Okay. So at this stage, please do allow me to drop this thing, which we assume that it is sitting on the left. Whenever I have this, let's assume it is actually sitting. Otherwise, we'll just actually waste a lot of time in just writing the same thing many times. Okay, so that's what I have. And L dot p, as you can imagine, it can be expressed as L plus p squared minus L squared minus p squared with an overall factor of half. That's what it is. Okay. And remember that what your d0 is. d0 was L squared minus m squared. d1 was L plus p squared minus m squared. So I can express my L squared and L plus p squared in terms of the denominators and the masses. So what does that mean? That means half d1 minus d0 minus p squared. Okay. So because m square actually gets cancelled between these two guys, so I have d0 minus d1 of p squared. So what I was able to do, I was able to write down the dot product of loop momentum with the external momentum in terms of the propagators or the denominators, and that if I can do that, then then the left hand side, okay, is half, and I basically now divide by d0 d1, I get 1 over d0 minus 1 over d1 minus p squared over d0 d1. And remember, with an understanding that I have this d-dimensional integration sitting on the left. Okay, what is this d0? This 1 over d0, this integral is 1 over L squared minus m squared. This is 1 over L plus p whole squared minus m squared. We have just evaluated this. Okay, we have just evaluated, we know the answer of this. The question is, what is this? This also looks like the same integral, except the fact that L plus, instead of L I have L plus p. Okay, but remember that in d dimensions I can use actually the shifting property of the integral, which is finite, and therefore this becomes just this. So under the shift, this integral is same as this, and therefore I get rid of these two, and what I have is minus half p squared over d0 d1, which is what? b0, right? Because p square is outside, so minus half p square times b0. The 2-point scalar integral. Okay, this one. That's what it is. So we know basically how to solve this. We still have not actually dealt with this, but the time will come, we will talk about it as well. But we know basically, if we have solved one, so we can actually hope that with some techniques we can solve this also. But let's not actually worry about that right now. And therefore, p square times b1 is equal to this, which implies the unknown coefficient b1 is minus half b0. Okay. So what we have just done, we have shown you that this tensor integral can be expressed in terms of a scalar integral. Okay, and it so happens that in this case the 2-point tensor integral is written in terms of 2-point scalar integral. I will basically write down an exercise that you should do in case of actually different masses. So in case of different masses, we can discuss this in tutorial if you want. It's very simple. Let me just to do this. 1 over p squared a0, I'll explain the notation. A0 of 0, this is for different masses, plus m1 squared minus m0 squared minus p squared times b0. Let me explain the notation. So this is 1 over d0, this is 1 over d1, and remember that since I have different masses, d0 is L squared minus m0 squared. I'm just differentiating the masses, and this was L plus p whole squared minus m1 squared. So this is a mass difference. Okay, so this is still the L plus p is irrelevant. It is just L, but the difference is that this is a 1-point integral with mass m0. This is with mass m1 squared. So they exist, and we know basically their expression. Okay. That expression had basically m squared sitting outside, so you will have basically non-zero term sitting here. So this basically gives us a better, you know this, but this basically gives us a better picture of reduction. What reduction means, that this tensor integral can be written in terms of scalar integrals, okay, with 2 propagators, and scalar integrals with 1 propagator, which are lower. And what we are going to see, this as you go for higher point, meaning propagator more than 2, you are going to see basically that the tensor integrals, they can be expressed in terms of scalar integrals of the highest number of denominator and all possible lowest number of denominators. Okay, so if you have 3 propagators, that tensor integral would be written as in terms of scalar integrals with 3 propagator, scalar integrals with 2 propagators, which can arise in different ways. For example, so this notation that I will be actually using later also, in the bracket it tells me basically how I have obtained 1 point function from 2 point function by removing which denominator. So one says basically d1 is missing, and this says basically 0, the d0 is missing. Okay, so that's how basically you get the lower structure. Okay, so I think the steps are clear. Therefore, I will not do the second rank completely, but rather basically I would write down the results, and it is important to basically do them because it gives you the confidence of handling these objects. Okay, and also see, this is actually in some sense what we have done. This is what actually Ravi was doing with the currents. Okay, he was using basically Lorentz covariance to write down all possible structures, and there basically we had several objects like gamma mu, q mu, and so on. But for us basically is the external momenta which are available, so that's what actually we are doing. So let me quickly just guide you to the this second rank tensor, which also basically is part of the integral we had taken. And let's just actually practice what we want to practice, that what is the structure on the right hand side. Again, I have got basically only one momentum, so I can certainly write p mu p nu with some coefficient, let's call it actually b11. But now since I have two ranks, I can basically also use the 2 rank tensor that is available, that is g mu nu. So metric tensor can also be used, b00 g mu nu. So this becomes actually your most general structure which you can actually write on the right hand side. And so you have come across now 2 unknown coefficients, b00 which is the coefficient of g mu nu, b11 which is the coefficient of p mu p nu, and you want to now extract b11 b00. And what you can do, you can basically get one equation by multiplying g mu nu. Okay, remember that in d dimensions, all the algebra you have to do in d dimensions. So g mu nu contracted with g mu nu is actually not 4, now it is d, and with p mu. So you do these 2 contractions, you are going to come across actually 2 equations, and you solve for b0 and b11. Okay, so you get that b00 as b11. I will not write, I will just write actually b00 just to emphasize certain points. So a00 plus m squared b0 plus half p squared b1. Okay, similarly you can obtain for b11. Now what I have basically, I have written down b00 in terms of b0 and some a0 and b1 which we already know. Okay, so it's like recursively you are going to basically use the result that you have obtained at a lower point function. Yes.
So this reduction that you are doing, it is for basically for one loop sort of this bubble type processes. So let's say it is here, it is it seems doable. Okay, if we go to, let's say, one loop pentagon, there you will have 4 independent momentas.
Yes.
And for them you have to write so many tensors.
Yes.
So can here in the left hand side you have one equation, can all the like coefficient can be extracted out or not for the pentagon or
right, yeah. So I will basically address maybe in the next class the same thing. So up to 2 point things are quite straightforward, but if you want to continue this with a higher point, even for example say 3 point, we will see basically there are difficulties, and it is better to basically again use some other mathematical tricks, which, as you said, what your objective should be, that you want to apply an operation which directly picks up the coefficient of a particular Lorentz structure. So that can be done. So, and we will see, we want to do it actually systematically, and we will do it. Okay. So so the point is, similarly you can have the expression of b11. So couple of actually remarks here is that, first of all, like you see, everything is basically in d dimension. Okay, and so for example you have an overall factor which depends upon d, and these quantities, these are actually divergent quantities. These are actually ultraviolet divergent quantities. So when you set this limit actually 4 minus 2 epsilon, you have to basically carefully do the calculation, because in the process of say simplifying in d is equal to 4 minus 2 epsilon dimensions, you have actually order epsilon terms sitting here, right? 1 over d minus 4 is like, sorry, d minus 1 is like 1 over 3 minus 2 epsilon, which is like 1 over 3 1 minus 2 epsilon by 3, which is 1 over 3 1 minus 1 plus 2 epsilon by 3, okay, and so many other terms, okay. And this order epsilon term is basically going to hit the 1 over epsilon pole and give you the finite contributions. So taking care of actually all these finite contributions systematically is important, as you can imagine. In fact, basically they have consequences for various symmetries of the theory, like gauge invariance and so on, okay. So the other point is that when you do all these operations, okay, you have to also pay attention carefully to that what are the basically, so say internal line masses, what are external lines and so on. Say for example, the result that I have written down, okay, is actually less visible here. If I could have actually written B11, which I would like you to basically do it and we can discuss in the tutorial, but this whatever I have done, this actually holds if the virtuality of the external momenta is not 0, okay. So p squared is not 0. So often you will see that when you obtain a result, you specify what are basically internal line masses, whether massive, massless, and what are the external virtualities, because as we will also see, I mean, in fact actually the best example is B11. In B11 actually you get this term 1 over p square and so on. So that expression actually doesn't actually reduce into the case of p squared is equal to 0. So for the case of p squared is equal to 0, you have to basically start from the beginning and impose that, and you are going to get entirely different expression for p0, b00 and b11, okay. And as you go for higher point function, it is important again. So we will see that when I say basically 2-point function or 3-point function or 4-point function, there are basically so these are classes. In that class you have to specify the result would be different for different cases. For example, all the external virtualities are 0, some of them are 0, internal lines are massless, some internal lines are massive, and the most general result that you can write, it may not actually work for all these actually possible cases, okay. So this is one of the intricacies of loop computation, that you have to classify your result by specifying what are the internal line masses, what are the external line, whether they are massive or massless.
So if
Yes.
more than one loop,
Yeah.
if some irreducible scalar product comes in the denominator, how do you deal with it? Is it there is a way to deal with such?
So what do you mean by irreducible?
Like for example, which comes from auxiliary propagators, which are not in my set of propagators.
So at one loop this never
that
happens.
never happens. But in two loop, can we use these procedures?
So yeah, since in two loop what you said that doesn't happen, therefore there are limitations. Okay.
This has a limitation of two loop at higher.
Yes, at higher loop this has a limitation. So I think if Rana was here, he would have probably had planned to give specific lectures on two loop. But we maybe in one of the tutorials, or if in last lecture, we can discuss that part at least, that why things which lot of things basically at one loop, they don't actually work at two loop, and therefore one needs actually a different way of looking at those objects. Okay. So in fact the result that we will derive for one loop case, that would be partially true at multi loop level. In some way basically it won't be true at all. Okay. So yeah, maybe I can actually stop in 5 minutes and we can actually take up some questions. So,
Make one
yeah,
remark.
yeah, please.
Q loop also you can have this kind of a tensor decomposition. However, the coefficients V00, V11, they will be in shifted damage. It's a mathematics, it's tensor decomposition. The answer has to be expressed in terms of only these tensors. It exists. The coefficients, if you look at it, these, those will be in shifted dimensions. So it's not correct to say that it's not possible to decompose. It's always possible to decompose. You start calculating these B's, they will be in shifted dimensions.
Yeah, but my
Otherwise, how can you prove that in any integral, after integrating the loop momenta, has to be expressed in terms of external momenta.
Yeah.
The Lorentz covariance tells you that they have to be as success like P mu, P mu, G mu, or more number of vectors and tensors. The coefficients cannot be calculable in terms of just multiplying this and that.
Right.
Reducible, irreducible. But there may be some other alternative methods to compute them. If you compute, those will be scalar integrals, but in shifted dimensions, not in 4 minus 2 epsilon, but it could be 6 minus 2 epsilon and things like that. So there is some literature on that actually. But such tensor decomposition is possible. I mean that's fine.
Yes, okay, yeah, right, yeah. So yeah, this part is actually general because this is simply based on Lorentz covariance. It's about basically extracting the coefficients.
So the choice of basis would be difficult in that case.
Choice of basis means, at the end of the day, you'll have, given it a rank 2 tensor, there are only two unknowns, V11 and V00. You can also redefine, G mu nu minus P mu P mu and P mu P mu. That's also another basis.
Yeah.
And independent of basis, the coefficients, number of coefficients is constant.
But the coefficient will be dependent on the choice of basis.
Obviously, choice of basis. That is correct actually. But the question is whether, I don't know, this question was actually whether tensor decomposition is possible or not. Is that what your question is?
Yes.
That is also
That is possible.
Possible.
But there is no unique way.
There is no unique way actually. There is no unique way. You can, it's like, in some vector, vector space, it could be, the dimension is same. How you write your unit vectors is up to you. It's always possible.
Okay. So last couple of remarks basically it's about higher point function, for which basically we need to we will see basically that this method becomes a bit inefficient and one needs to basically organize it better. So what we are talking about, I had basically this kind of integrals, right? And and if you try to basically write down their amplitude, you are basically going to come across structures like L mu, L nu, L mu, say 1, involving in this case D0, some D1, some D2, while in this case D0, D1, D2 and D3. So 4 propagator and 3 propagator, that's what basically you are going to come across. And the question is again, can these be again expressed in terms of say the corresponding scalar ones and the lower point scalar functions? The answer is yes, but one can actually see some difficulty if you want to just continue with this way of doing it, okay? And the difficulty appears if you want to say look at say for example this L mu, L nu with 3 propagators, that basically I want to denote as a notation something like C mu nu. And now it's a 3-point function, so I have got actually 2 linearly independent momenta to work with, unlike in the case of 2-point where I had only 1. So let's say basically they are P1 and P2. So if this is L, this is actually P1, this is L plus P1, and if this is actually P2, this is L plus P1 plus P2. That's what my D0, D1 and D2 are. So again, if you want to basically decompose like it, now this time you need to utilize all the 2 linearly independent momenta. So you have some C00 G mu nu, plus you will have combinations of P1 and P2, right, which I want to basically write as Pi Pj mu and nu sum over I and j, which goes from 1 to 2, and corresponding coefficient Cij. Okay, that's what basically your general structure would be. Of course, because by definition this integral is symmetric under mu nu exchange, that basically tells you that Cij is equal to Cji, so they are same. So what you have basically, you have 4 independent coefficients, C00, C11, C12 and C22. That's what actually you have. Now if you want to continue that procedure, you can actually, it's not that it is actually impossible, but the point is you can actually appreciate that if I want to say, for example, what I have got P1, I have got P2 and I have got G mu nu to now multiply. So I can set up basically 3 equations to extract actually 4 coefficients. Okay, and this is where basically you are going to see a problem. And if you go basically say, for example, higher tensor integrals, you are going to basically going to see this becoming more and more severe. Okay, so what is actually better in such cases, and this is what basically I would like to discuss say in the next lecture. We will do it in the case of actually 3-point, and the formalism that we will develop, you will be able to apply, you will be able to see that how easily it can be applied to 3 dimension. And the idea would be that you construct suitable projectors which, when applied on this, okay, of course they would be function of external momenta, they basically pick this or this. Okay, uniquely, they uniquely basically pick C00 or one of the coefficients Cij. Okay, but this actually we will do tomorrow, and yeah, till then actually if you have questions we can actually discuss. Question or comments? Because there are many students for whom it is a bread and butter, and they must have actually learned something which they want to basically share with all.